Hello everyone! In this video, we will continue examining the topic of reflection, the wave behavior of reflection, and in particular, we will examine reflection at a plane surface, or two-dimensional reflection. Okay, so as before, reflection is the change in direction of a wave at an interface between different media, such that the wave returns to the original medium. The most famous case of reflection, the Christina Aguilera case, if you will, is the case of light reflecting in a mirror, okay, or perhaps off the still water of a pond. But this kind of reflection occurs in all kinds of waves. Reflection in sound is known as an echo, and reflection occurs also as water waves. But we're going to focus in on reflection of the type you might think of in the case of light, okay, for a beam of light. So if you take a light ray and you shine it in at a surface, you'll discover that that light ray, as it comes in, bounces off in a very particular manner. In point of fact, it bounces off such that the angle of incidence, theta I, is equal to the angle of reflection. So if it comes in at a steep angle, it leaves at the same steep angle, something like this. If it comes in at a shallow angle, it will leave at the same shallow angle. Okay? This is visualizing or representing that light wave using rays. And this is the traditional diagram for two-dimensional reflection, because it very clearly shows that that angle of incidence is equal to the angle of reflection. One thing I should note is that when we say the angle of incidence and the angle of reflection, we measure those angles against this line here, known as the normal. Okay, that normal is the line perpendicular to the surface, and it's quite traditional to give the angle of incidence relative to the normal rather than relative to the surface, which is what these angles would be. Of note is that sometimes the IB plays dirty and will give you this angle when in fact you need to use 90 degrees minus that angle theta I, 90 degrees minus the angle they give you to get theta I. So just be careful. It is worth noting that this is fundamentally a wave phenomenon, and to understand why it occurs, okay, we're actually going to use a wavefront diagram, something like this. Okay, but before I do that, I want to show you a quick simulation of those wavefronts coming in, because this diagram, as you can see, can be a little bit confusing. So this simulation is falstad.com/ripple. It's what's called a ripple tank, and it has lots of options. You're welcome to pull it up and play around if you like. I'm using the option called refraction here, but I am going to use it to demonstrate reflection only, and we'll come back to that. So what this simulation does is it sends a set of wavefronts at a boundary, and those wavefronts all reflect off. And it's important to recognize here that this is the same phenomenon we were just looking at, except this is showing more, like you might see on the surface of water waves, how that reflection comes about as a result of the wave phenomena. And in particular, I want you to notice that as these wavefronts come in, the near side of the wavefront hits the boundary before the end of the wavefront hits the boundary. That is, that left side of the wavefront hits the boundary before the right side hits the boundary and bounces off first. And that is responsible for the phenomenon that the angle of incidence is equal to the angle of reflection. You can see that the near side hits the boundary and sets up the angle as it comes in and then goes back out again. This is easier to see in the simulation sort of as it moves, although in 1 second I'll demonstrate what I was just talking about. So if I come back here, we can see that I have shown those incoming wave fronts as this light blue color here, and the outgoing wave fronts as this dark blue. So these light blue wave fronts come in, and then when they reach the boundary, they reflect offwards as those dark blue wave fronts. And the key idea here is to recognize that as this particular wave front comes in, the near side hits the boundary first. And if the near side hits the boundary first, it also reflects off first. And so if we see these outgoing wave fronts, this end, the left side end, is the end that has hit the boundary first. And that's ultimately responsible for the fact that the angle of incidence is equal to the angle of reflection here. Two other things which may be obvious, but I just want to reiterate, there is nothing special about the particular angle of incidence drawn. It does not have to be 45 degrees, although often that's shown. So any wave coming in at any angle will exit at the same angle of reflection that it came in as for its angle of incidence. It is also important to note that this line right here, that normal line, is not a special location. So if the wave hits to the left, it will exit at the same angle, just as if it hit over here. So that dotted line is not a special place. It just is drawn wherever that ray and that wave have hit that boundary. That is more obvious in the case of the simulation. It doesn't matter where it hits, that wavefront will move off in the expected direction.